All right, good evening, everybody. It's a pleasure to welcome Mike Tice here today. So I've known Mike for almost 30 years now. We were undergraduates together at the California Institute of Technology. Mike graduated there in 1997. He then went on and did a master's in geology at Duke and his PhD at Stanford. After that, he was a postdoctoral researcher at California Institute of Technology for a couple of years. And then he moved to Texas A&M, where he was an assistant professor and then an associate professor, and now is working as a full-time research scientist. And Mike is a member of the Perseverance team. He's an expert in geobiology by training, so his original work has mostly been here on Earth, but he's going to talk about how we can take knowledge from developed here on Earth and use it to understand life in the universe, especially using Perseverance. So whenever you're ready, Mike.
Great. Thank you, Tom, and thank you for inviting me out here. And thank you for everybody showing up. I'm seeing some names here that I've known even longer than Tom, which is impressive. So nice to see you all. In just a second, I'm going to jump into showing you some videos from when Perseverance landed on Mars and some images that were taken shortly after that. But I wanted to orient you before we jump into all the crazy stuff. So today we're gonna start out with general things about landing in Jezero Crater and talk a little bit about some of the new things that we had to do to land where we did, and then talk about what really gets me excited about this mission. So there's a lot of science that's going to be happening with Perseverance, but what really gets me up in the morning excited to see imagery and other data coming back from the rover is where this mission fits into how we look for life in the universe. And so we'll step back for a big picture view there and then back down to the rover and look at both what it's capable of doing and what we're planning on doing with the science payload over the next several years. So on to those videos. And you'll see where this still came from in just a second. So let's go here. What you're going to see first, just to help you make sense of the video you're going to see after this, is a simulation and an artist's imagining of what the landing would look like from outside the rover. So watch this, you'll get an idea for what's happening later on when we see the footage from the actual rover. But all the fake geology is going to be replaced by real stuff in just a second. So let's get started here. Okay, so this is back February 18th as Perseverance is approaching Mars. It's in right here attached to its cruise phase shell, which gets detached just before it enters the Mars atmosphere. Currently, it's traveling faster than a bullet and about to hit the atmosphere. And in the space of 7 minutes, it needs to slow down to where it can actually land safely on the surface. So in it comes, still at supersonic speeds. There's very little Martian atmosphere to actually slow the entry vehicle down. So there are several ways that you'll see it slowing down here. First is a parachute after the initial slow down from the heat shield. Then we drop the heat shield. And what happens now is the rover is starting to image the landing area with radar and cameras. It drops down from the parachute and goes just on the sky crane, the jet that you see here. In this part, it's actually diverting to a safer place to land. We'll talk about that a little bit later, but this is the first mission to Mars that's had the ability to change where it's going to land as it comes down. As it slows even further and gets closer to the surface, the rover detaches on cables from the sky crane, gets let down, cables detach, And off goes the sky crane. Okay, this is all just to orient you to what you're about to see, which is the real stuff. Let's just get rid of that. Okay, this is what things actually look like. These are from cameras on the rover itself. You're going to hear audio from the mission command at JPL. We didn't have any of this video as the rover was descending, of course, because, well, two things. It takes light time to travel from Mars back to Earth, and these are big video files. They actually had to all be uploaded to an orbiter and then downloaded through the Deep Space Network back to Earth so we could actually see these things. So all these things have been put together by JPL people afterwards. Okay, so here's actual imagery of the actual video of the parachute deploying. That was one of the first indications that the rover was not going to die, so there was applause there. There goes the heat shield. Everything that you see here is inside Jezero crater. This is where we're going, but you can't see the landing site yet. As it gets closer, you can start to see more of the features that we're going to be interested in. This pile of rocks over here is going to be really important, and right in about here is where we're going to wind up. And actually, I'm going to pause here for just a second, because even as we're watching this, there was the Mars Reconnaissance Orbiter able to see all of this from orbit. We have still images of this. This is Perseverance descending on its parachute right here, ultimately down to its landing spot. This big pile of rock over here is what I was saying is going to be interesting later, so keep that in mind.
Mike, what's the spatial scale of this video right now?
It's changing continuously as we descend.
Yeah, I mean, like right now, roughly, is it like miles or?
Yeah, the one side here would probably be about 3 kilometers, 4 kilometers or so.
Okay.
And we're just about to divert to a safe landing spot.
Here in 50 Bravo. We have about 30 meters per second, altitude about 300 meters off the surface of Mars.
And we're a lot closer to the surface than it looks. Okay, and for orientation, you're seeing dust and sand being blown around by the jets from the sky crane right now. This view up here, I believe, is going to be from the rover looking up at the sky crane. This is the sky crane looking down at the rover.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
I must have seen that video about 20 times now, and I still enjoy watching it. But right at the very end there, you saw the sky crane jet off away from the rover. And what it's doing is just taking its remaining fuel and flying off as far away as possible so that it doesn't crash on top of the rover itself. But what's really kind of cool is as it was going off, the cameras on the rover were working, and we actually see off in the distance over a ridge here, this is smoke coming off from where the sky crane crashed down. And this is imagery from the next day from Mars Reconnaissance Orbiter again of the rover in its landing position with dust blown out by the sky crane off to both sides. So there were a couple of things that went on that were really fairly remarkable and different from previous missions, and allowed us to put the rover down very precisely, pretty much where we wanted it to be. And I want to talk about that briefly for a second here, because this winds up being really important to the mission. So I'm going to refer to landing ellipses, and that's just because I can't, when I talk fast, I can't refer to it as anything else. But a landing ellipse just refers to the fact that when you send a probe from Earth to Mars, or really anywhere else, you can target a place that you want to be, but you can't do it with complete precision. So there's some uncertainty in where you wind up landing. Back when Tom and I guess when I was in college, Tom had just graduated, Mars Pathfinder was sent to Mars, and it had an uncertainty of where it wound up landing that you can't even put completely on this image of Jezero crater. So it was 124 by about 44 miles wide. We got better over the years. So by the time we got to 2012 and Curiosity landed on Mars, we decreased the size of that ellipse down to close to 16 by 12 miles. 2021, when Perseverance landed, we were dealing with a landing ellipse only about 5 by 4 miles wide. So to give you some idea of the sizes that we're talking about here, here's where you would all be if you were actually at Astronight in Lubbock at Texas Tech. And if we tried to send a rover this way to wind up at Astronight, these are the ways we would potentially land. So this is back in 1997 with Pathfinder and Sojourner. You know, we could try to hit Lubbock, but really there's an uncertainty that is a pretty decent chunk of the Texas Panhandle there. You could wind up all the way up in Amarillo. And that rover in particular hardly traveled any distance at all. You really had to accept where you landed in order to do anything. Now, Curiosity was significantly better. You can see that you're when you but trying to get to a place like Astronight, the rover in its 9 years since it's been on Mars has only traveled the diameter of this landing ellipse. So it could potentially take several years for you to wind up where you originally intended. Whereas you can't see it here, but that tiny little spot down next to Lubbock there, that's the Perseverance landing ellipse. It's about the size of downtown Lubbock. And Perseverance is capable of traveling far greater distances autonomously than the previous missions. Basically, you can get there in about a month, potentially. So we really invested a lot in getting where we wanted to go. The other thing that was remarkable about this mission relative to previous ones was this terrain relative navigation. When I talked about diverting to a safe spot, this is what was going on. And basically, this is a system that allowed us before the mission began to identify places where we definitely didn't want the rover to land because it would land on a big slope, like on this cliff face over here and die, or it would land in a boulder field and have a chance of landing on a boulder and die. or it would have a chance of landing here, and maybe it would land okay, but we'd never be able to drive out of it. And so an important part of targeting this area was being able to take that hazard map and have the rover identify, once its heat shield was gone, it was able to take pictures looking down, places that we didn't want to land. And if we were heading there, then it would divert to the right or to the left of the current path and hit something that was safe. So originally, as the rover was coming down, it was actually heading for a landing right in around here in this red zone. And what terrain relative navigation allowed it to do was to divert off to the right into the small safe zone over here, and away from the heat shield and the parachute that continued along in a straight path and ultimately wind up someplace safe. The thing that's really remarkable about this is we landed about 5 meters, about 15 feet away from where terrain relative navigation told it to land. That's about the distance of an average car. And the rover itself is about the size of a VW Bug. So imagine taking a VW Beetle, sending it off to another planet, and landing it. It's the equivalent of landing a VW Beetle in a highway in Lubbock, Texas. We really wanted to get to this particular place, and there was a lot of technology that wound up going into getting us to someplace safe where we were within driving distance of really important things.
I have a question for you, Mike. How important are the winds on Mars for determining how accurately you can land? Is it all based on the initial trajectory having some uncertainty from launch, or is it based on stuff that happens after it gets to Mars?
The winds definitely affect things. In fact, some of the drift that you saw in the video there were from winds. And so, yeah, that definitely affects the size of the landing ellipse. Part of what, I'm not going to be able to get too deeply into this, but my understanding, part of why the landing ellipse was able to shrink was changes to how the parachute got triggered initially. So I think previous triggers were based on atmospheric density, so elevation roughly, and now it was triggered by velocity, and that was a big part in shrinking the ellipse. Oh, and I should say that to everybody on here, feel free to ask questions as we go along. I think probably the easiest way to get a question answered is to type it into chat, and Tom is going to keep track of what's going on over there. But if you see something that's particularly interesting, or something where you have a question, let me know, and I'll try to get to it. Okay, so why did we invest so heavily in getting to one specific place? In order to, and the questions we're trying to answer by going to Mars. And as Tom mentioned up front, I'm a geobiologist. I care a lot about the history of life on Earth. Another title that I've carried throughout my career is astrobiologist. I really care a lot about the search for life in the universe. And a lot of what I've done is to try to think about how what we see on Earth can tell us about the probability of finding life elsewhere. And as you'll see, we're about to expand that thinking to Mars. Okay, so I'm going to jump into stuff that I'm absolutely certain people in this department are going to know a lot more about than me. So this is kind of a fun place to stick out my neck and show just how ignorant I am about things. But let's do it. It'll be fun. So think about how common is life and where should we look at? Where should we look for it? One of NASA's chief strategies in looking for life other than on Earth is they call it is first cut, look for planets sort of like Earth and that they're rocky and that they orbit a star at a distance and temperature at which it's possible to have stable liquid water at the surface. So they've even gone so far as to classify those planets as habitable. So the question is, given that definition, how many of those habitable systems are likely to have life on them? And one way that I like to think about this is sort of within our stellar neighborhood, within 100 light years of Earth, so with other stars, their light takes 100 years or less to reach us. How many of those stars are likely to have life around them? Well, one of the important and amazing results that has come from recent observations of planets orbiting other stars is an estimate of how common habitable systems might be. And it's currently estimated that within 100 light years of Earth, there could be around 1,500, 1,500 planets orbiting them that have water on their surfaces. Now, if life is rare, if it's incredibly unlikely to develop on one of these worlds, then it's quite possible that even with all those stars with habitable planets around them, we're the only one that has life. On the other hand, if life is really common, and essentially NASA is right that when you have water, you're likely to develop life, then we could have around 1,500 living systems within our neighborhood. Or if the answer is somewhere in between, if there is some probability between 0 and 1 that life evolves on these planets, then maybe, say, hundreds of planets. So the question is, looking around us right now, what can we say about that probability?
Mike, there's a question in the chat, and I don't know if you want to answer it now or put it off, but the question is, can you talk about MOXIE? What if it's not able to produce oxygen from CO2? Does that derail plans to send astronauts to Mars in the 2030s? And what other alternatives are there to produce oxygen?
I will point at MOXIE later on and tell you a little bit about what it does, but I'm not going to be able to answer most of those questions.
Okay.
It might be a fun thing to chat about later.
Okay.
Okay, so one way to answer this question about how likely life might be is to look. What you here is a timeline of Earth going from today over here on the right, all the way back to the formation of Earth 4.6 billion years over here on the left. And one thing that's really striking, water has been around for most of that time. And for most of that time, life has been around too. In fact, we don't know how far life goes back because really, as soon as we have rocks in which we're able to look for signs of life, we find it here at around 3.9 billion years ago. So life evolved very early. For most of that time, really from here to about here, most of that life has been microscopic. Some large things started evolving a little bit later here, but things that form the kinds of fossils that we're used to thinking of, things like shells or dinosaurs or even later, came in around here. So most of that time, life has been very small. But what you might conclude, and in fact, many people have suggested looking at this, is that life happened so early on relative to when we had water available that microscopic life in the universe might be very common. In other words, look for planets with water, there's a good chance that microscopic life may be living there right now. But just about any scientist will tell you, we're looking at, we're trying to extrapolate from a case of one. What we'd really like to be able to do is compare to something else, and ideally something else that we can go investigate in some detail. Now, Mars might not seem like the best place to do this initially. Mars is not water rich. It's got a really thin atmosphere that doesn't allow liquid water to be stable on the surface right now. However, we have lots of evidence that liquid water has been present there in the past, and particularly here in Jezero Crater. This is a composite image of Jezero Crater that you can actually access by going to Google Earth and clicking on a button that makes it Google Mars. But what you see here is an old river valley that entered Jezero Crater from the west over here, and then another river valley leaving Jezero Crater and flowing downhill towards another impact basin. So the fact that we have both an inlet and an outlet channel here tells you that at one point, this entire crater was filled with water, and it was in fact Lake Jezero. And over here, there's a body of rocks that look an awful lot like modern deltas in lakes. So this would be where sediment came in from the river and was deposited as the river slowed down entering into the lake. So at some point in the past, we think Jezero looked more like this. Well, that's pretty neat, because really what we're saying is that if we want to look for another place where we can test this idea that life essentially follows water, is by stepping back in time on Mars. The cool thing is that if you're a geologist, this is essentially what you do for a living. You go and you look at rocks and you step back in time and you try to figure out what was there. I'm going to skip past this and just mention that basically by looking at Jezero, we're able to look at an interval of time. It's probably not all this time, but some part of it, towards the end of when Mars had liquid water on its surface, at a time when we know there was life on Earth, and ask, was there microscopic life present then too? And a big part of why we went through all that trouble with the precision landing, we wanted to get to the rocks that tell us the story and allow us to step back into time and ask that question. Okay. So let's look at the tools that we're going to use to do that. I'm going to start out by giving you just sort of a general overview of what's on Perseverance, then talk about this instrument here. It's my favorite because it's the one that I work on. It's called Pixel. And then talk about a little bit about what we're going to do with this stuff. So somebody was asking about MOXIE earlier. That's one of 3 instruments that I'm not really going to talk about much today. But they are doing other important things that are part of the why you send a multi-billion-dollar probe to Mars. It's never to answer just one question. MOXIE in particular is being sent to see if we can generate oxygen from carbon dioxide. We know we can do that here on Earth, and we want to demonstrate that we can do it on Mars, so that we can use it both for rocket fuel and for breathable air to send humans as explorers. META is a fancy weather station that's there to answer questions about the current atmosphere, and hopefully tell us more about its current state and how it got there, or why there's less atmosphere than there is now. RIMFAX is a subsurface radar that's capable of telling us generally what's beneath the surface, what we can't see. But the ones that I'm going to focus on today are the things up on the mast, MASTCAM-Z and SuperCam, and then the ones over on the arm, Pixel, Sherlock, and then there's a drilling system that's not labeled here, but you'll see it on the images. And these are going to be the main instruments that we use to answer these questions about life. So up on the mast, these 2 cameras are part of the MASTCAM-Z system. This aperture here is part of SuperCam. And for reference, this thing is about the size of a cereal box. Okay, MASTCAM-Z takes stereo images. So we're constantly getting images back that we look at with 3D glasses to get a better idea of what we would see if we were there on Mars. But the other thing it's really good about doing is zooming on distant things to capture features that would otherwise be really difficult to see. So we landed here about 2 miles away, 1.5 miles away is this butte surface. This is about the size of a 6-story building from base to top. And you can actually map out layers of rock in here. And this is one of the things that I really like playing around with. SuperCam is actually capable of doing that a little bit too, but its main specialty is taking really magnified views of especially nearby rocks. This one's from 3 meters away. This target's called Moz. And we're actually able to zoom in from that distance and see what I would normally see if I walked up and put a magnifying glass on the surface. The other thing it does is it has 2 different lasers that it fires at rocks to figure out what they're made out of. So this particular laser system that you're seeing data from is intense enough that it actually converts part of the rock into plasma, and it takes images of that plasma to measure their color. And from that, you can tell the elemental composition of the rock from an amazing distance. Out on the arm, again, we've got Pixel and Sherlock and the drilling system. Unfortunately, there isn't much to show you from any of those instruments yet. We're not going to be able to completely test these things out until we're finished with helicopter operations about 2 months from now. But I can tell you a little bit about what they do. Down here, Sherlock and Watson are for taking really high resolution images up close to rocks. And one of its main jobs is going to be to look for organic molecules, potential remnants of past life. The drilling system here is both for sanding off rock to look down below the surface of crusts, and also for collecting samples. So, things about the size of this pencil or a piece of chalk. We're actually going to be collecting samples of rocks and bundling them up for a future mission to go back and return to us. And then Pixel, its job is conducting really high resolution compositional maps of rocks. And you'll see some examples of that in a second. But one of the first pieces of data that we've got back from Pixel is basically demonstrating that it's alive. This is what happens when you take a really expensive instrument and you take images with the dust cover still attached. So here you're seeing the inside. This is the backside of the dust cover. These lights are spots from a laser array that allow us to tell how far we are from a rock as we're analyzing it. And this X-ray spectrum tells you what the composition of the paint is inside the dust cover. It's mostly zinc. So the key message here is that Pixel is alive, and we're hoping to actually do this with rocks in the near future. The last part of this looking is that the rover is capable of doing some amazing things to figure out geologic context, how were rocks formed, and to do some things that can give us hints that there may have been life preserved in those rocks. But ultimately, we want to do more detailed analyses with these things by sending them back to Earth. So sometime in the late 2020s, we're going to send a follow-on mission with a smaller rover that will go out and collect samples left behind by Perseverance, load them onto a launcher that will send them up into Mars orbit, where they'll be captured and sent back to Earth. So sometime in the 2030s, there will be other scientists, probably some of them still off in school at the moment, who will actually do the really detailed work of digging into these rocks and finding out more about them. Really quick before we move on to the mission, I want to introduce Pixel to you. So this is an image of Pixel as it was sitting in the fabrication lab before it got attached to the rover. And you can see some actuators on here, some arms that actually tilt Pixel back and forth to look at things. This is what it looks like attached to the arm now on Mars. For size, to lead team that actually built the instrument in the lab, and the woman here taking the selfie with the instrument in the background is the principal investigator. She was the one who originally had the idea to build this crazy thing, and is going to be leading the science team as we analyze data. But to get to what Pixel will actually do, you saw earlier, Pixel stands for Planetary Instrument for X-ray Lithochemistry, which I really think of as just a way to make Pixel a word. What it actually is an X-ray microscope for seeing the compositions of rocks. So in this example, we've got a rock from my lab back at A&M. You can see it's made up of several different kinds of rock or different kinds of materials in there. And it would otherwise be fairly difficult to tell what it is just looking at an image on Mars. Pixel is going to be able to draw grids or lines or maps across things and be able to say things like, well, these light layers up here have a lot more calcium than this layer down here, or than these layers down here, or draw maps. So in this particular example, these bright spots correspond to sand-sized grains of a mineral that we would actually collect on the spot and want to send back to Earth, because they could be used to tell the age of this particular layer of rock. Pixel is able to measure the abundances of elements really from sodium to uranium, but these are the things that we expect to potentially see in abundances that are large enough to be able to measure on Mars. You'll notice that carbon isn't one of these elements, and we're constantly I often get this question, how are you looking for life if you can't detect carbon with this instrument? The answer is that many microscopic life forms are able to concentrate or move around some elements in rocks, depending on how they were making their living. And so in these particular examples, I zoomed right past these earlier, but these are examples of some of the earliest life on Earth, where to detect the concentrations of these elements and confirm that they were in fact formed by living things. Pixel actually works by pointing at rocks. It shoots out an X-ray beam thinner than the diameter of a human hair, and then rasters it across the rock in maps or lines or grids, generating the kind of data that we saw just a second ago. Okay, so those are the instruments.
I got a question, Mike. Are these relatively high energy X-rays? Is that why you can't see anything lighter than sodium?
The highest energy X-ray coming out, one of these photons would be about 28 kilo electron volts.
Mm-hmm. What's the lowest?
It goes all the way down to 0.
Oh, okay.
So you could potentially see carbon. In fact, I'm buying an instrument that will allow me to do this in my lab back at A&M.
Yeah.
But we have to filter out some of those X-rays before they hit the detector. And to have something that's stable enough to go through all the shaking, you have to use a beryllium window that doesn't allow those X-rays to pass through.
Okay, all right.
Okay, so we landed over here. Ultimately, by the end of our roughly 2-year prime mission, we want to wind up at the head of this old delta, and with an extended mission, push on into even older rocks up here in the highlands that we know a lot less about. But in the meantime, we're going to be able to hopefully address an awful lot of questions. And this is going to give you a rough outline of what we're going to be doing. Really, for the next 2 months, I haven't talked at all about the helicopter, but we actually sent a helicopter to Mars with Perseverance. And for those 2 months, we're basically checking out places where the helicopter can fly safely. We're going to drop off the helicopter for the first time ever. No science, but an awful lot of cool stuff. So we're looking forward to that. Our next step is going to be to look at the rocks that you see generally around in here. And one of the first questions we're going to be asking is just, what are these rocks? And we're especially interested in finding out, how do they relate to the delta up here, and can they possibly tell us about the times when the delta was active? These might be rocks that we're going to be able to return to Earth and date. And we've got really 2 choices of how we do that. We can take this northerly route, or we can take this southerly route. We don't know how we're going to go yet. But once that happens, we'll do something roughly like this. Drive up over the delta here. Oops. Just back up and say these are the kinds of rocks that we're in here, looking around at the landing site. But as we actually get up into the delta, now we're going to be able to start asking some more questions about life. We've got some very geological questions that will help us to contextualize that question. Under how much water was this deposited? Was the lake high at the time that this was being deposited, or was it low? And maybe these are primarily formed under rivers. We're going to be able to figure that out by looking at them up close. At the moment, this is all we can really see of them from the distance. Just to get a better idea for how they formed. We're going to drive up to what may have been an early lake shoreline and ask, was there life living in the very shallow water or up along the shores at that time? And when we get off to here, we'll drop off our first cache of samples as one potential thing that sample return could grab and send back. All of this ultimately to sort of fill out that initial picture that I gave you of habitable planets. These are all things that exist now, but by going back into the past with Perseverance, we want to add ancient Mars to the catalog of potentially habitable planets and ask, was there life there, as our first chance to increase our sample size to 2 and get an idea for how common life might be. And that is the end of what I had prepared for here. I'm interested in hearing some more questions. Looks like we've already got one.
Okay, so let's give Mike a round of applause, please. Okay. All right, and now, yeah, we're happy to take whatever questions we have. So we have one from Thomas Kupfer. What do you think would be the smoking gun that there was microscopic life on Mars without a doubt?
So the funny thing about looking for past life anywhere, especially if it might not be something that you can go out and find running around on Earth today, is that there's rarely a single piece of evidence that you classify as a smoking gun. What you want to find is a series of confirming pieces of evidence that something was doing stuff that living things do. So evidence that it ran a metabolism, it was getting energy from its environment somehow. Ideally, some evidence that it reproduced itself. So if you find a fossil of a microorganism, you'd ideally like to see other things that look very much like it nearby. Some evidence that it was doing things that normal non-living sediment or whatever the environment it was growing in didn't do. So there are maybe some fairly simple things that you can imagine. If we get back organic molecules that are fairly complex and very difficult to make abiotically, and you found those organic molecules in an environment where organisms could have lived, but not in neighboring rocks where they couldn't have lived, that would be a really good piece of evidence. We're not going to be able to get all of that with Perseverance. But there are some other things, like some of the samples I showed you, that we could probably collect evidence with Perseverance that would make me about 80% confident. And once we got the samples back to Earth, we'd be a lot more confident by building up that collective case. It's something you have to do in place and when you get samples home.
Okay, Josh Hall, I see you have your microphone open. Did you want to ask a question?
No, I'm riding my bike home. Sorry.
Okay. All right. Anybody else have some questions? I have a follow-up to that, Mike. I know there's some ideas out there that even if we find life on Mars, it doesn't mean that it originated on Mars, that because rocks get knocked off of planets and onto other planets, we could have had life that came from Earth and went to Mars. How would you determine that you had life that uniquely evolved on Mars?
Oh, gosh, that'd be difficult. And in fact, there are other ideas floating around out there that it would be even more likely that life would have originated on Mars and made the trip to Earth. Especially if it's microscopic life and all fossil, I think we have very little chance of answering that with this mission. What I'd have to do is actually send human explorers to Mars, people with a chance to walk around and collect evidence at a much greater pitch than what we can do with a rover, and potentially explore a lot more of the old Mars surface to get an idea if the things that we're seeing there were living the same kind of lifestyles that we see on Earth at the same time.
Oh, sorry, I'm muted. Are there plans for sending another rover mission before sending astronauts?
I think realistically, yes. So that, although not really a science mission, so there will be a follow-on mission to Perseverance that is intended to to collect the samples that Perseverance caches and send them back to Earth. Beyond that, we don't have plans for another rover. So a lot of this really depends on how much we're willing to stick to the idea of sending humans to Mars and making it happen.
Okay. What is the lifetime of Perseverance? Is there something which limits the lifetime, or could it continue to explore for years to come?
So the shelf-rated lifetime of Perseverance is 2 years, which is, I always laugh about this because every single rover that we've sent to Mars has gone well beyond its rated prime mission, and we fully expect Perseverance to do the same. past that, ultimately things have broken on or made more difficult to deal with that were fairly hard to predict. And I suspect that's what's going to happen with the rover. The power source is an MMRTG, so it's essentially a nuclear power generator that generates power from heat, a decay of plutonium, and that's going to lose us power generation at a rate of a few percent, maybe 2 or 3% per year. That's the most optimistic thing that could potentially limit us. Otherwise, it's something like a wheel stops working or something like that.
Okay. Are we collaborating with China or the United Arab Emirates to see what they're learning with their spacecraft that arrived there in February also?
People are certainly looking. It's not something that we discuss regularly on the rover team. And close collaborations with China are actually prohibited if you're funded by NASA. So that's a relatively recent thing that went through Congress. I think it's a little unfortunate if you're interested in science, but that's how we have to work.
Yeah, it's only bilateral. So if you get a third, if you get like some Iranians involved or something like that, then it's fine.
I'm gonna have to cut off this chat now, Tom.
Yeah.
See you later.
Yeah, no. I mean, we have it for the astronomy missions too. That bilateral interaction with China is prohibited, but any multinational thing is allowed. They might be a little stricter on some of the things with spacecraft, but the congressional law allows any kind of multinational thing.
Right. Now, we do have far closer collaborations with Europeans, as you'd expect. And Pixel itself, the camera in it was built in Denmark. And so most of the people involved in the really detailed image analysis are in Denmark. We have a big team off in Australia that's also working on a lot of software, and will be doing a lot of geological interpretation with us.
Okay, and we also have the question that the same person asked about Moxie. If you said you might be willing to discuss that a little bit more after the talk.
Well, just in the sense that I'm interested in hearing people's thoughts on it. Heard of contingency talk about what happens if Moxie doesn't work. Certainly, my impression of this technology is that it's so stable on Earth, and Moxie is, it's bulletproof enough that we stuck it on a rover and put it through that entry that you saw. That we fully expect this thing to work on Mars, really as a demonstration, but I don't know what happens if it doesn't. And again, for everybody out there who's wondering, Moxie is the instrument that's generating, it will be generating oxygen from carbon dioxide in the atmosphere of Mars. The reason we want to do that is so that we can generate rocket fuel in place instead of transporting it all the way there, and have some other stuff for astronauts to breathe.
Yeah, I would probably agree with you, Mike, that there's no reason to expect it wouldn't work, but NASA is just ultra conservative about things that are mission critical, that you actually have to prove it works before they let you say it will.
That's right. There's a long path of technology demonstration, and actually getting descent to Mars on a rover is a pretty good sign that this sucker's going to work, and they just want to confirm it.
Yeah. All right. After Mars, where else in our solar system do you hope to look?
Boy, I think some of the most intriguing places to look next would be some of the icy moons in the outer solar system. So places like Enceladus, and gosh, I'm blanking on
which planet does that orbit?
I'm having trouble coming up with the names and planets here on Zoom, Tom. Adam says Saturn. I believe Adam.
Okay. Yeah, okay. Isn't Titan also supposed to have enough tidal heating that it could have?
Yeah, so Titan around Jupiter, super interesting place. Both both from the perspective of water and the subsurface, but also because it's the only other place in the solar system where there's a sedimentary geology happening on the surface right now with a liquid. So there, yeah, Adam says Titan, also Saturn. Thank you, Ezra. So it has liquid hydrocarbon lakes. It has hydrocarbon rain. It has dunes from different processes happening on the surface. It's a great place to go look at a very different kind of geology. And if you want to get really crazy, there are people who speculate that you could potentially have very different life forms living in hydrocarbon lakes there. I think it's really fun to think about what those might be like, but yeah, that'd be pretty neat.
Okay. Do they have an idea of what types of clay could be in or around the Jezero Delta Plain?
Yes, from orbit, they're able to get estimates of this. Clay mineralogy has never been one of my strong points, and so I'm not going to be able to list them off to you here. Gosh, no, I'd have to go back up and look up which clay minerals have actually been spectrally identified. Certainly smectite is one of them. So one of the important things about the clays that we see there is that many of these clays could be generated by weathering reactions in a time when there was more water up in the highlands. And so it's generally consistent with the idea that Jezero Lake existed and was collecting sediment from a time when things were wetter.
Okay, we got totally off topic, but just curious of your thoughts about Planet 9 existence.
I have no thoughts on that. I'd be more interested in hearing Tom's thoughts on that, or some other people.
Or maybe Thomas.
Well,
Please.
well, there was just a paper published where they claim that this kind of overabundance of these objects, which potentially could indicate Planet 9, is statistically not significant. So I think to be honest, the scientific answer would be it's up in the air. I don't think we can exclude it, and I don't think there's any smoking guns evidence that it actually exists. So that would be my honest answer.
Yeah. Okay.
And as a side note, there's an awful lot in planetary science that sort of exists in that gray area because there's just a lot of stuff we're really interested in. So a while back there was a lot Venus. For those of you who weren't following the news about that, there is a particular kind of molecule that was found in the atmosphere of Venus potentially, and on Earth. One of the main sources of phosphine is life. So really wild idea that maybe there were microorganisms living in the atmosphere of Venus producing phosphine. There's a lot of follow-up going on about that, and one of the possibilities is that phosphine wasn't really detected there. It was an artifact of observation, and even maybe more fundamental idea, at least in my mind, is that we don't really know all the things that are going to be producing phosphine out there, and so life might not be the right answer. Similar questions about the atmosphere of Mars. There's been methane that's been found there for sure now, but we have very little clue about what could be producing it. Life is one intriguing possibility, but there are lots of other possibilities.
I got a question just about the landing issue, going back to that. What are the typical wind speeds on Mars? Are they similar to Earth or faster?
I think they are often similar to Earth, but of course the atmosphere is a lot thinner there. So sometimes they will pick up more, but they're generally not blowing things around quite as much as what they do on Earth.
Okay.
In fact, one of the active ongoing pieces of science that Perseverance and some of the more recent rovers have been doing is trying to figure out why dunes form on Mars. You would predict based on wind speeds and the density of the atmosphere there that would be awfully hard to move the sand around that's necessary to form dunes, and yet it happens. And so one of the things that we're looking forward to doing is taking movies of moving sand at the same time as we collect atmospheric measurements with META. And that's, again, one of the surprising things that you'd think we know, but we don't yet.
Okay, another one. All right, I think these are two questions that go together. Is that right, Michelle? Are there questions about winds or
Yes,
dust?
yes.
Yeah. Okay. Do you want to ask it? You're certainly
Sure.
welcome to speak up. Yeah.
Yes. Can you hear me okay?
Yeah.
Yeah, I was just wondering if there were concerns about winds or dust impacting Perseverance. So is META going to help it to kind of have early warning of any potential storms, and will it have time to avoid that?
So unfortunately, the rover is way too slow to actually avoid anything. It really, gosh, it'd be awfully nice to make a movie of this dust devil that's approaching us. But dust is something that we think about constantly. Dust on Mars is really, really fine. It's sticky. It gets on everything. And so we're already looking at images coming back of things like calibration surfaces and photographic and compositional calibration surfaces, and saying, gosh, look at all that dust. Fortunately, we've been dealing with this for essentially every Martian mission that's gone up, and so we've got ways around it. But yeah, there's no way the rover can escape dust.
Okay, so what is the highest speed the rover can go?
I'm not sure what the highest just straight away speed would be, but if you give us a relatively flat area and we tell it to go someplace, we can make 200 meters in a day. So, eighth of a mile, sorry. And that is absolutely trucking for a rover. And keep in mind, this is in some ways like setting a self-driving car down in a boulder or a dune field, right? So, we feel pretty good about those speeds. We need every bit of that speed to explore what we need to explore and to collect enough samples to make a sample return be fun and interesting.
Okay. I got a question. How do they send the data back? Is it a radio link or is it using some other kind of technology?
Yeah, it's radio. The rover can send signals back directly, but mostly it's sent through relays from orbiters around Mars.
Mm-hmm. And is that a limiting factor to how much data you can collect?
Yes, hypothetically. It was more of a limiting factor for previous missions. But evidently some of the newer setups are allowing much greater transmission rates than we've had previously. But to give you an idea, I said I think that Pixel was mostly going to be doing its maps overnight. Part of that is X-ray spectroscopy is a fairly slow thing, and so we need all that time. It's also going to be generating a lot of data. And so part of the original idea was that if we need to actually see results from something we look at, we need to do fairly short measurements and do them during the day, so that at night that data can be uplinked and quickly downlinked for us the next day to make decisions with it. But for those bigger files, potentially there would be times where those have to come back to Earth in chunks, and so potentially multiple days. And you can imagine that for a sampling mission where a major thing that we want to do is drive up to a rock, sample, move off and collect the next sample. First of all, you have to get things back quickly enough to make decisions. The original thinking was a lot of those overnight measurements weren't going to be useful for decisions about sampling. They'd just be useful for information about the area. But we're now starting to think that most of those are going to be able to come back in one pass. And if not the next day, then certainly the day after that, we'd be able to start using it.
Okay. All right. So I want to mention, I think Mike will probably be happy to stay and continue to answer some questions. But we also have some students who are doing some demonstrations. And I'm going to post the link to the webpage if you want to join some of those. And then hold on a second. So let me find that link. I'm going to paste that into the chat window here.
Yes, thank you.
And so you can go and watch some of those demos. I think the one that Linka is doing with Tesla coils, she should already be ready to go. And then I'm going to have to drop off briefly and set up Arvind for the sunset and the glass demo. And then Manuel is going to do something with spectroscopy. And that link may have to change. We're going to check on that. And then about a half an hour from now, it'll be dark enough to do observing from the campus observatory, and that'll be in this room where we are right now. And I think Valya will let us know when it's dark enough and when we have something ready to go.
Sure.
So let's thank Mike again.
Thank you, Mike.
Thank you all.
And so I'm going to log off. I'll be back in about 5 minutes on
Okay.
this one after I get Arvind set up.
So are you going to stop recording now?
Oh, yeah.